Great. All right. Hello, everybody. Thank you so much for joining. We're right here at 12 Eastern time. I think we are going to go ahead and get started. Well, welcome everybody. Thank you again so much for being here and for joining our first webinar in our new Electrochemistry for the TEM webinar series. My name is Jen McConnell. I'm the product manager here at Protochips, and we are really excited to host this series because so many researchers in the Protochips community have been working with electrochemistry for the TEM for years, 4, 5, 6, 7 years and more. And they've gained so much knowledge about the technique that we thought it would be great to try and aggregate at least some of that knowledge for those that are just entering the field, thinking about entering the field, thinking about adding this technique to their research repertoire, and et cetera. That, like I said, our community has been investigating this technique for longer than any other community on the market, and we're really proud of them. And there's a significant amount of valuable information to be learned about materials using TEM and observing dynamics on the scale that the TEM can enable. And so our community is going to share that value, what they've learned and how they got there. So before I introduce our presenter and star of the show today, I have a few housekeeping things I'd like to touch on. First of all, feel free to sign up for as many webinars in the series as you would like at protochips.com/webinar. You can also see the link in the chat right now. We'll be posting registration links for the webinars that are coming this spring and summer. We'll have those registration links posted somewhere around the beginning of the year. So for housekeeping, everybody in this webinar is going to be muted due to the number of registrants and attendees that we have. So if you've got any questions for our presenter, please enter them in the chat box, and during the Q&A session at the end, I'm going to go ahead and read them out to him, and we'll do as many as time will allow. I'd also love if you wouldn't mind filling out this survey that's going to pop up at the end of the webinar. That's going to give us information on how we can provide more interesting and educational content for you in the future. And you're also going to receive after the webinar a short video in your email about our newest machine vision software platform called Axon Dose. You're going to hear a lot throughout these webinars in this series about electron dose and monitoring it and managing it and quantifying it and reporting it. And in the field up until now, there is some inconsistency and some differences on how people do this. And Axon Dose is a way to take the variability out of it, and so that way you can quantitatively measure, track, and report dose from the microscope on a pixel by pixel basis, no matter which microscope you're using or which lab you're in, so across the community. Okay, enough of that. Let's go ahead and introduce the star of the show today. So today we have with us Dr. Yao Yang. Dr. Yang received his Bachelor's of Science in Chemistry from Wuhan University in 2015 and his PhD in Chemistry from Cornell University in 2021. During his PhD, he was co-advised by Professors Hector Abuña and David Muller and worked extensively with Professor Francis DeSalvo. His PhD research focused on the design of precious metal-free fuel cell electrocatalysts and the characterization and understanding of their reaction mechanisms employing multimodal operando analytical techniques. This includes operando electrochemistry STEM and synchrotron-based X-ray spectroscopic and scattering methods. As a Miller Fellow at UC Berkeley, which is happening from last year through 2024, he works with Professor Peidong Yang to investigate electrocatalysts for the conversion of carbon dioxide to liquid fuels in an effort to provide an atomic and molecular level picture of dynamic electrocatalytic processes with advanced analytical techniques. He received the Wentic Award, which is the highest graduate award in chemistry at Cornell in 2020, the Cornell High Energy Synchrotron Source Student Research Award also in 2020, and the Microscopy Society of America Student Poster Award in 2019. We are so honored to have you here, Dr. Yang. I'm going to go ahead and pass this to you because this is all about your research and what you've learned. So when you're ready, go ahead and share the screen and take it away.
Great. Thank you so much, Jen, for the kind introduction. And I want to first thank Protochips to work so hard to actually have this webinar. Really to our community Today I would like to kind of share you some of our recent progress on doing quantitative electrochemical like studies in open liquid cell STEM. Let me share my screen. Jane, can you see my screen and hear my voice?
Yes, sir.
Great. Okay, let's get started then. So, so this talk basically is kind of gonna have two main keywords. The first one is really about quantitative electrochemistry. The second one is how we do operando study in liquid cell STEM. So this field really has taken off since the pioneer study by Francis Rose now at MIT. I would like to more focus on the electrochemistry side of this new analytical technique. So as you can see here about this kind of really the progress going from conventional ex situ measurement to in situ and operando measurement, we are using basically the fish as a research analogy to make efforts to see how catalysts evolve in operating conditions. At the beginning, I would like to sort of give you an overview, basic where this term operando category came from. So operando spectroscopy was first actually reported by Banyuas and Wackhausen in the early 2002. It's almost 20 years ago. Back then, the emphasis was really to emphasize want to make a difference from in situ measurement. So the main focus was back then on Raman and the IR spectroscopy, and it has since then basically really begun to make an impact in the catalysis community and also chemistry community in broad. So in this study, I would like to kind of define operando really as the analytical techniques that provide comparable electrochemical behaviors to standard electrochemical cells. Meaning, what I mean by comparable is basically a redox couple that occur at the same or similar current density, which basically is the reaction rate under same or similar applied potentials, that is the driving force for reaction. So with that, I also want to point out basically since last year we have this a review in acidic catalysis to kind of to cover the recent progress about operando methods, in particular TEM and X-ray studies. So I can give you a few examples, basically what the difference between ex situ, in situ, and operando methods. So ex situ really means off-site. Basically, typically you're working on dry or frozen samples in high-wave conditions. That basically applied to most of the conventional SEM, TEM, and other probing microscopy and XPS as well. In situ means basically on-site or in position. So that basically to simulate a part of working device and reaction condition. This actually begin to get some insight of the sort of the catalyst in operating condition. A typical example can be environmental TEM, and ambient pressure XPS is another quite a common technique you would see from literature. For operando, really means operating or working condition. So that means real-time operating condition in a working device. And it really, the reason we see so few study in the literature is because it really require complex and expensive devices and quite often require the TEM and the synchrotron beamline. Ideally, we would prefer to even have a product detection that will now we would see actually several very nice example from Oak Ridge. They begin to do product detection for gas phase TEM. And another example would be the operando X-ray spectroscopy that are used for fuel cell device. You can put the entire fuel cell device in a beamline to do real operando study. So with that, I would like to kind of get into the technique I'm going to introduce today. That is mainly operando electrochemical liquid cell scanning transmission electron microscopy, which I basically make it short as E-system. And this one in this talk, I will also highlight the recent progress, how we incorporate the 4D STEM capability in this E-system setup. So on the left, you would see basically for typical E-system setup, we will have a liquid thickness on order about half micrometer, and this basically has great technical help from prototypes. And on the right side, you see a typical design of the 3 electrode system. We have working, counter, and the reference electrode all in the same cell. So because the such confined space of sub-micrometer liquid, we cannot use a regular commercial reference such as silver chloride, or cannot or have a salt bridge in this case. So it's commonly you would see the platinum pseudo reference used for the liquid cell TEM study. It's not only true for the prototypes products, but also for many other suppliers for liquid cell TEM. Platinum reference is basically very widely used because it's easy to manufacture by the nanofabrication. So with that, I would like to basically sort of provide a tutorial talk on the electrochemistry, specifically while using electrochemistry of platinum as a fingerprint to really probe where we are in terms of potential. So I want to kind of point out applied potential for electrochemist is as important as scale bar for the electron microscopists. Basically, you would much prefer scale bar for the TEM image, as we would prefer a reliable potential reference point for the electrochemist. So here I'm going to basically show you kind of example. On the left is actually cyclic voltammetry of platinum single crystal, which basically can see depends on the surface phase. You see distinct different features for platinum 111, 100, and 110. And in a polycrystalline platinum, you would see basically all 3 features. And depends on the surface orientation, you may have a different ratio 110 to 100. The important fingerprint is the position of platinum 110. Which is about 0.10 volt, what is RG, which stands for reversible hydrogen electrode. That's basically the commonly used potential scale for electrochemist. So in this case, basically, I'm going to first show you how do I basically calibrate the potential for platinum pseudo reference. Let me basically get into, before I show you a lot of the electrochemical data in liquid cell TEM, I want to take a step back to show you basically what is the best case scenario for platinum reference. In this case, it's a standard 3 electrode electrochemical cell, which actually is very simple. You have actually a platinum wire as the reference, and also platinum wire as counter, and also platinum as a working. This is all platinum electrode. So we basically simplify the reaction. In this case, actually, because we're using H cell, we can minimize the effect of working on the stability of the reference electrode. So over here, you are seeing basically the difference really is basically we are shifting the entire curve from basically when we're using silver chloride, that is standard reference electrode, to platinum pseudo reference as a platinum wire. So you see the difference, and basically in this case we can work out the potential difference between platinum and silver chloride. In the bottom part of this slide, I'm showing you basically this is a very convenient potential conversion scale. Basically, that you can see the comparison. Eventually, we can put where is the potential for platinum pseudo reference electrode. Basically, in this case, here's the difference we are seeing, and also the standard hydrogen electrode is the absolute 0 reference point. It's always 0 by definition. So where we actually can basically know where is the potential for the platinum pseudo reference is on this potential scale. This is a pH 1, and which basically is almost starting point one often do for platinum calibration in liquid cell TEM. If we move to pH 7, this actually is in a buffered solution of carbonate. Actually, carbonate solution, you can see we can basically go through a similar math and eventually figure out where is the potential for the platinum oxide of platinum in this case. And it's also basically you can see then the difference for pH 13. We are seeing when you see the 3 a different pH value, you see the difference, the potential difference between silver chloride and the platinum reference is getting a bit smaller. So basically this also eventually would kind of tell us the pH dependence of platinum pseudo-reference electrode. So I'm going to give you a summary slide, and basically given the 3 different pH values, we can build a linear correlation of the potential platinum pseudo-reference versus SEG that's 0 by definition as function of pH. We see a strong linear correlation with a slope of 53 millivolt. So this number actually is important because for classical non-steam shift, we expect a slope of 59 millivolt. And given all the experimental measurement errors, we actually think this is close to a non-steam type pH dependency for the platinum reference. Basically, the translation is the potential of the platinum reference is really pH independent on the IHC scale. So like IHC scale for the electrochemist, when we use platinum reference for the liquid cell TEM, the difference, basically the potential of this reference does not change as function of pH, and which basically I do have one comment later on this claim, and so this result would be summarized in we have a review paper in Current Opinion Electrochemistry that came out in early 2023 that would have covered a much more in-depth discussion on the calibration of platinum reference electrode, and also basically what's the effect of the pH, the cation, anion. You would basically see a discussion on that in this review paper later. So then let's look at the stability of the platinum reference electrode. Basically, in this case, surprisingly, actually, we observe a remarkable stability for the reference in the H cell. Basically, now we can deconvolve the platinum reference electrode from the confined space in liquid cell. In this case, we only worry about the stability of the reference itself. So for the first 1 hour, we see virtually no shift, and for the following 1 hour, we see a shift as small as 5 millivolt. So this tells us if the environment for this platinum reference is really stable, we can expect a very stable potential point for the platinum reference electrode. So this basically sort of give us some confidence, even though it is pseudo, meaning not real electrode, but actually we do have a decent reference point in terms of applied potential. So then let's now begin getting to the real world. Basically, the moment we begin to work in liquid cell TEM, because such confined space, which basically really limits our kind of control in terms of the surface pH and also diffusion and mass transport in the liquid layer. So on the left is basically the pioneer work done by Megan. Actually, this will be almost 10 years ago by now at Cornell. Back then, the collaboration between Bruni and Muller group actually tells us we begin to have a basic collaboration about basically if we are using the platinum 110 as a reference point, we actually can see we eventually basically are getting a potential conversion between the platinum reference electrode and RHE in terms of 0.85 volt. And you basically another perspective look at this basically a CV is at below minus 0.8 volt. At any moment you can evolve a hydrogen bubble. That's basically hydrogen evolution on platinum occurs at about 0 volt versus RHE. On the right side is basically the recent work I have done. You actually can see the position for the platinum reference in the H cell. Well, there's still a difference. Basically, for H cell, where we are basically observing platinum reference versus RHE about 0.94 volt. So we see a little discrepancy between a liquid cell TEM and H cell, and performed by 2 different people. And actually, you will see the difference more common in literature. So we do see about a 0.1 volt difference. And the question is basically, is this difference real? Or like basically, should we trust more the measurement from H cell? We eventually need to work in liquid cell TEM. Basically, we want to see basically roughly what is the error bar of applied potential we have in this case. So I'm just going to give other two examples. I mean, we have numerous examples basically for platinum CV in liquid cell TEM. I'm just basically giving two extreme possibility. On the left side, we do see basically a conversion 0.8 volt. On the right side, we are seeing a conversion 0.9 volt. So in practice, after screening many examples, we basically conclude that in practice that's actually a potential conversion 0.8 volt and with error bar as big as 0.1 volt. So this basically is kind of, I think, the first important message to the audience. And then let's basically looking at how is the stability of this platinum reference electrode in liquid cell TEM. On the left, basically, we are seeing in some cases it's actually fairly stable. I mean, and then in other cases, we do see a potential shift of as big as 100 millivolts within 10 CV cycles. That's actually in a short time of 3 minutes. So this actually basically is concern actually in the confined space of liquid cell TEM. We do sometimes observe a potential drift basically as we perform electrochemical measurement. So what has caused this? And there can be several reasons. And one possibility is basically the electrochemical reaction on the working and the counter electrode actually are changing the surface pH. You already notice that basically how sensitive the potential of platinum reference is to the pH. Basically, a slight change in surface pH can actually cause the potential shift, which is basically we want to give you a realistic expectation of what you can achieve in liquid cell TEM. So another perspective looking at this basic instability in terms of potential. Now I'm instead of using a buffered solution, I'm using unbuffered neutral solution, which is 0.1 mole sodium perchlorate. In this case, basically, this was performed in each cell, but for platinum solid reference electrode. So given the potential conversion, we are expecting basically a potential of 0.7 instead of 0.6 volt for this reference in unbuffered solution. That basically translates into a surface pH of 4.3. So the electrochemical reaction for the platinum on the working electrode actually are changing the surface pH slightly, which basically actually an acid concentration of as small as 50 micromole can cause the pH changing by actually from 7 to 4. It's basically just kind of give you a sense basically how is the potential shift correlated to the pH change. So then I'm going to basically cover one kind of now realistic example. Is basically we can not just working on platinum. It's beautiful electrochemical behavior, but we want to basically get into real world application. So one example I have been working at Berkeley is basically to study the copper nanocatalyst for CO2 reduction. So in this case, I'm showing you two examples of the cyclic voltammetry. This would correspond to redox couple from cuprous oxide to metallic copper. In both cases, basically, if we are relying on the potential conversion 0.8 volt between platinum and Rg, we are basically getting this redox couple located at 0.4 volt versus Rg. This basically is true for the prototypes liquid cell TEM holder, which we take the same holder to same design, but basically with different liquid thickness. And this actually is X-ray holder designed by prototypes to the synchrotron beamline at advanced light source. You actually also see a potential conversion about 0.4 volt versus Rg. So how reliable this is when we compare to standard measurement. So I'm going to basically show you this is a beautiful electrochemical study of copper single crystal done by Paula from University of Copenhagen. Actually, you can see basically there are lots of signature here, and the one I want you to pay attention to is basically the oxidation peak of copper surface. And we actually can see in either 0.1 more hydroxide or 0.1 more carbonate, we do see this occurs about 0.4 volt versus RHE. So we do have basically the conversion from platinum, study of platinum actually can apply to other electrochemical system. And the fact we are seeing this in both like pH 13 and pH 7 actually really is basically suggests the potential conversion for the previous study is reliable. So with that, I'm now going to shift the gear to basically two examples like I have done in my PhD, and also briefly touch the most recent work I have performed at UC Berkeley. So the first example I want to cover is basically we are moving from the study of platinum to the study of copper. This basically would eventually come down to the research field called under potential deposition. UPD actually is basically a classical example, almost textbook level example of how basically metal deposit on foreign substrate, especially when the copper deposit on a substrate that basically had higher work function than copper. We would see the deposition is much easier, require less driving force than the copper deposition on copper. So this basically gave us actually a chance to really evaluate this electrochemical liquid system to perform both quantitative electrochemistry and also quantitative image analysis. So I'm basically showing you the system we're having basically a gold nanocube with basically exposing 100 facet, and we're actually now showing you the copper deposition. This tiny bump here, that is actually the UPD of 1 monolayer copper, and this larger peak actually is the deposition of copper, bulk copper deposition on copper. This happens about 0.28 volt versus SHE. So and then with the adding of chloride, we're actually also seeing a slight change of the behavior, and this does have a dramatic influence on the deposition of copper. So I'm basically here I'm showing you one example. Basically, this is EOS elemental mapping. In STEM mode, we actually are seeing basically 5 angstrom copper deposition on the surface, because actually there's this beam is penetrating a 6 sample. We do expect the beam broadening. This actually the real copper thickness will be likely 1 monolayer. So when we get into the bulk copper deposition, you can see basically here we are making slightly thicker copper layer on the gold surface, and since then we can grow like gigantic copper clusters with the gold as the seed. So that's basically in terms of the deposition of copper on gold surface. Now let's look at the comparison between the H cell and its system. So on the left, basically we're actually observing the deposition peak of 0.3 volt versus SG. I want to clarify that the copper deposition itself can serve as internal calibration point. Basically, the deposition peak is actually quite reliable once we specify the copper concentration, scan rate, and also the presence of anion. So, and basically that's kind of how I perform the potential calibration, which basically I expecting we are seeing potential about 0.3 volt in the liquid cells here. So this high quality of electrochemical measurements basically can give us the really the chance to assess basically how well defined electrochemistry is in liquid cell TEM. Basically, we can plot the peak current of reduction potential as function of scan rate. On a log scale, we are seeing actually a curved relation. This suggests the deposition from copper ion in the solution to metallic copper on surface is diffusion controlled. That's no surprise. We expect a diffusion controlled process for copper deposition. What is surprising though is basically for stripping process, if you strip metal from the surface of the electrode, because the surface control process, we would expect a linear correlation, but instead we are also seeing a square relation. This can be explained now. Instead of having a surface control, we have the diffusion control, but for the counter anion too, that we need to maintain charge neutrality in the solution. So basically, now with that level of like electrochemical data, we actually can basically go through the Randall-Sandwich equation. That is a way based on the relation between peak current and loss current. We can figure out what is diffusion coefficient. That is basically on the order of 10 to the minus 5 square centimeter per second in the liquid cell TEM setup, and in the bulk measurement, we are seeing 10 to the minus 6. And this basically was also earlier reported by Raymond Unisek from Oak Ridge. Basically, we actually are seeing a similar diffusion coefficient for copper in the solution. So this really suggests that we do have a well-defined diffusion control, the behavior in the E-system. Then basically, I want to kind of just show you an example. Basically, what kind of reaction kinetics can we track in the liquid cell TEM? Basically, here we are basically control the applied potential, basically going from a mild potential minus 0.1 volt to intermediate and to aggressive potential minus 0.3 volt. After the first electrochemical measurement, we can strip away the copper. At the same location, we can basically perform the deposition at more and more negative potential. So in this case, basically, you would notice I'm using a very low concentration of copper and also very low beam dose to minimize beam damage. You see basically for minus 0.1 volt, we are seeing planar growth, very slow. For basically intermediate potential, we are seeing this island-shaped growth into the solution. Then what is really exciting is basically what happened basically is the growth at minus 0.3 volt. You see this particle was basically left out. At 200 seconds, it was electrified and it began to participate into reaction. And this is clearly caused by electrochemical potential, not caused by beam damage. So this actually gave us a chance to analyze dendritic growth because we are in the STEM mode. So really the image intensity is basically quantitative. So by doing that, we actually can quantify the growth rate of crystal relying on the STEM image intensity. In both cases, in terms of crystal growth rate, we are seeing a square relationship. And this actually also, from the crystal growth perspective, we are also observing well-defined diffusion control process. And then my second example is really basically to explore the technical capability of Operando E-system, and not just doing imaging, but also involving elemental mapping and also structure analysis with 4D STEM. So this study actually basically started from basically unexpected observation. So there was at the beginning of the project, we basically trying to push the limit how wide the potential we can open, and to kind of really see basically what's the limit in terms of potential we can apply this system. In one case, we went to basically very negative potential. It's below minus 1 volt. You don't quite often go there, right? It's basically this would be crazily negative for electrochemists, and kind of make basically my colleague feel quite uncomfortable. So then you see really basically after this potential, you are evolving basically enormous amount of hydrogen bubbles, and instead we are seeing basically we're seeing something funny on the surface of the bulk electrode. We are not supposed to change the surface of bulk platinum, and platinum is basically rated as one of the most stable metal under any condition. But we are seeing this kind of mysterious amorphous structure on surface. So we think what could happen when we apply such negative potential for in the liquid cell TEM. Actually, when we basically went back to literature, we actually are really basically in this kind of very century-old like problem, and also it was actually it would basically get into the category of cathodic corrosion. Cathodic basically means like reducing potential, and we can corrode noble metals if the potential is sufficiently negative. So back then, in as early as like 19th century, Fritz Haber actually was reporting the formation of metallic dust. If you basically simply connect the platinum wire to the negative electrode of the battery, you actually can see particles are falling off from the electrode surface. Back then, basically, this study was simply by analyzing how much the mass loss from the cathode, and so since then this field really has been pushed by Professor Mark Cooper from the Netherlands, and they actually are basically providing now a better understanding of this really in basically intriguing process. So we're seeing here, this basically is a modified Popper diagram, and we are basically seeing in terms of the thermodynamic stability of one metal, in this case platinum, as function of potential and pH. So in most of the case, we are basically platinum. The reason platinum is noble metal is basically it is in its immutable region. We are very stable. Platinum is happy being here, and quite often platinum would experience oxidizing potential, which we refer as anodic corrosion. That is very common in many like fuel cell study involving platinum catalyst for the oxygen reduction reaction. Very few study actually would even think about this. Basically, go below potential below -1 volt, and eventually you begin to trigger the corrosion of platinum once again. So this is not just basically like basically a bizarre reaction to think about, which basically nowadays basically for many electrochemical reaction, in particular CO2 and nitrogen reduction, that does involve structure evolution of nanocatalysts under sufficient negative potential, which can easily go below -1 volt versus SEG. So my study basically can show you what is happening. At the beginning, we have this kind of beautiful gold nanocubes on the surface of platinum electrode, and during corrosion, we are seeing we actually are really consuming the gold cube, are ejecting a whole bunch of particles, and in this case, we begin to see a hydrogen bubble forming near the working electrode. So as you can see here, basically this basically is the electrochemical behavior of basically, as you can see, we do see accumulation of reaction intermediates, which we think could possibly be metal hydride informing the platinum nanoparticles. The important thing I want to point out is basically at about below -1 volt versus actually we see the dramatic drop of current. So in this case, this actually would correspond to the formation of a hydrogen bubble and the creation of a thin liquid layer. The liquid thickness was estimated to be about 100 nanometer by years measurements. You do see this dramatic improvement of resolution going from thick liquid to thin liquid, and we begin to track like the dynamic basically the particle reconstruction and coalescence, and also the migration as well as the attachment. Here we can see the two particles over here. So we are extremely careful in terms of the beam dose. We do want to minimize and also ensure no beam damage during electrochemical measurement. So we're at fairly low beam dose for this study. Actually, for most of my E-system studies, we are basically way below the threshold of triggering beam damage to the electrochemical reaction. So because the creation of the thin liquid thickness, now we can go beyond morphological change by STEM imaging. We can begin to investigate what is element distribution. In this case, because both gold and platinum are very stable, we actually can see the formation of this heterogeneous alloy structure. So we first seeing a gold-rich ribbon grow on the platinum surface, and we see this kind of beautiful dendritic growth of like bimetallic alloy, which is about 1-to-1 ratio. So really what we're observing is the formation of the bimetallic alloy in a region which is typically not accessible to chemical synthesis, in this white region, which is supposed to be phase immiscible. But yet we can push the formation of this bimetallic alloy, and this is only possible because we are driving a highly kinetic process of cathodic corrosion. So with the last few minutes, I would basically like to brief touch the most recent progress in begin to introduce the first 4D STEM study in liquid. This is basically showing a crystal orientation map of gold platinum bimetallic alloy, and this map was basically acquired in liquid under electrochemical condition. As you can see from the high quality diffraction pattern, this basically, and we also ensure that the beam dose are basically even comparable to the typically one would do for accumulating dose in imaging. So this basically is only possible is because the great help from Dr. Yuxin Shao. Now he's actually he's moving to University of South California, USC, as assistant professor. So with that, I will basically kind of like say, now when we demonstrate we can do 4D STEM in liquid, basically this really opened the door to lots of exciting application in other renewable energy technologies. So one thing I want to briefly touch is basically our recent studies performed at UC Berkeley. We are using this operando electrochemical 4D STEM to identify the active state of metallic copper nanograin for steel structure. We see the evolution from the starting point of 0 volt to minus 0.8 volt. We are basically seeing the formation of this nanograin, and which could be serving the active sites. And when those nanograin exposed into air, we are seeing actually they rapidly evolve into the single crystal cuprous oxide. So hopefully by Christmas you will see this work showing up online in Nature, and we are very excited to share you. Now we actually can using this technique to push the frontier of energy research. So with that, I would like to summarize my talk, and hopefully I have shown you now we can use open STEM to do quantitative electrochemistry that is comparable to a standard electrochemical cell. And the important message though is the platinum pseudo-reference actually is actually not so bad. Actually, in quite a good case, it's actually a pitch independent reference electrode on the IH scale. This is really convenient. Basically, regardless where the pitch is, you will actually can trust this potential conversion of 0.8 volt. And although I do want to point out we are seeing basically potential inaccuracy about 0.1 volt, and we are working basically to basically improve the potential accuracy with with more stable reference electrode. The second one I want to point out, basically, as you can see from study of copper deposition, now we can demonstrate a well-defined diffusion control process in this confined liquid layer, and which basically enables us to do both quantitative electrochemistry and quantitative STEM imaging analysis. So I basically want to point out the deposition potential of copper. Actually is an internal calibration. You don't have to rely on the conversion from platinum anymore, but the deposition potential really depends on the copper constitution, whether you have anion or not, and also scan rate. So you need to be extra careful with using the copper as the internal calibration. Last, hopefully I show you that now we can begin to introduce this electrochemical 4D STEM to provide this really valuable structure information in liquid under operating conditions. So the last thing I want to basically to kind of let you be aware of that. So we would have a second webinar next summer to show you the correlative open study with E-system and also synchrotron X-ray, both hard X-ray and soft X-ray beamlines. So that's basically would be focused on the on the recent work published in Nature. And then the second is basically this at MM meeting next year for the PO1 session, we would have basically this wonderful in situ TEM session organized by CV and other colleagues. So in 2 years, we would have the Golden Liquid Phase EM conference, and that will be in Italy. I'm the co-chair of the GIS. If you are interested in submitting abstract, we would basically have this information available on the website in the near future. With that, I would like to first thank Peidong for basically give me this opportunity to keep pushing the frontier of the open system, and the wonderful support from the E-chem team of in Peidong Yang's group, and also basically the guidance from my co-advisors, Professor Hector Bruni and David Muller at Cornell. So this basically has extensive collaboration with the TEM facility at Cornell and Berkeley, as well as the Beamline facility over there, and also at Stanford. With that, I would pause here, be happy to take questions.
Thank you so much, Dr. Yang. Hold on. I apologize for that.
No worries.
I have an echo. Give me just one moment. Got like 3 screens going on here to make sure everything's going smoothly. So thank you so much, Dr. Yang. That was a fantastic presentation. There are a ton of questions here, and so I don't know if we're going to be able to get through all of them, but let me go ahead and get through a handful of them, and then I'll make sure to connect you with the specific people who have the questions that we can't get to today, so that you can help them get an answer and start a conversation, if that's okay.
Yep, sure.
But it seems like everybody really enjoyed it. So question number 1 from Paul. I have been sweeping the working electrode between negative 0.25 volts to 0.75 volts versus an SCE in a rotating disc electrode in an RDE. But the half-wave potential is around 0.7 volts. But when I read the literature, it looks higher. The ink preparation is fine, but I don't know why the half-wave potential remains low. Do you have any thoughts?
Jen, is he or she able to talk? Yes, I just want to kind of clarify the question. So I hear the term of half-wave potential, SCE, as the reference potential, if I remember correctly.
Mm-hmm. Yeah, versus SCE and RDE.
SCE, yeah, that's basically for other people, this is meaning saturated calomel electrode is a mercury chloride. Basically, I'm doing a quick conversion to IHE scale that probably would transfer roughly 0.9 volt versus IHE for the half-wave potential. So a general answer to that question is basically if you are working basically to benchmark the electrochemistry, especially for platinum, for like a fuel cell reaction, really that's the preparation of like the electrode is really critical. It's basically how you basically prepare the catalyst ink and what is loading and also thickness of the platinum catalyst on the glassy carbon can have impact on performance quite a lot. So basically, I think definitely feel free to send me an email. I basically can send you. I have a tutorial section in my PT thesis how to basically provide a standard protocol for getting reliable electrochemical measurement for that kind of application.
Thank you. The next question says in slide 20, so referring to your slide 20, if you want to go back to that. Sure. Are you comparing the first cycles during deposition or a higher cycle?
Oh, very good question. Let me go there. So basically, typically for copper deposition, the first cycle is often would clean the surface, and also which basically we call it like a cleaning process. So typically, where I'm often basically using the fourth or fifth cycles in this case. The stable CV cycles is what I report by default, unless otherwise specified.
Perfect. Next question. How does plasma cleaning chips affect the potential of the pseudo-reference electrode? Would the plasma clean versus the not plasma clean chips perform the same way?
Oh, that one is excellent question. I have not verified that. For all my studies, I always plasma clean the electrode. Basically, always self-consistent. The main point is to make sure the working electrode is fully hydrophilic. You have basically fully wet electrode. That is basically the main purpose of doing plasma clean.
Perfect. Next question. How do you calibrate the platinum reference electrode if you don't have a well-defined redox reaction in your system?
Let's see. I can go back to this point. I think the other question, basically, see if I can answer the question right. So we used to think the platinum pseudo-reference is not a well-defined redox couple, but in this case, basically, that refers to this non-stoichiometry of platinum oxide versus platinum. As far as we are concerned, in terms of potential conversion, we are seeing reliable non-stain type pitch dependency. So to some degrees, it is a reliable redox couple, as you can see here now. And I think probably what you refer to is basically, can we use copper deposition stripping? That is another like convenient well-defined redox couple, or you can use ferricyanide or ferricene in organic solvent. So yeah, certainly there's other like a way to use like a better defined. You can pick up your favorite redox couple and then basically make an effort to have rigorous comparison between HCl and the system. So what I want to show here is basically, because I have so much knowledge kind of built up for platinum. So with this, we basically can easily compare with other results in the community, and also basically using platinum has the benefit of can easily convert into the RH scale. That's the most widely used potential scale for electrochemists.
Great. Let me go ahead and do a couple more, and then I think we'll call it, and I'll connect you with those whose questions I wasn't able to get to, because they're adding on as you're talking. Can you add a bit more information about the corrosion of the gold nanocubes when they are in solution?
Let's see if I go there. So for the corrosion of gold cubes, I am not sure basically which aspect of corrosion, but certainly I think I can basically provide some like a little bit more details. Basically, the corrosion process also is basically essentially we are dissolving the platinum atoms from the electrode and injecting into the gold cubes. So it's really the molecular perspective of this process was not covered in this talk, and I do encourage you basically to go through our basic recent JAX paper. You will see much more details for that discussion.
Great. And then finally, let's take our last question here. Let's see. Thank you for the informative and interesting talk. Can you comment on the cathodic corrosion of platinum in regards to the mechanism leading to this phenomena? Is the term corrosion being used to describe degradation in general, or are you actually saying oxidation?
Oh, it's not oxidation. This basically is corrosion on the reducing potential. So yes, that's actually a very good question. So typically, if we don't specify corrosion metal as common as you see from the rusting of iron steel, that means basically the corrosion metal on the oxidizing potential basically by the oxygen in air. Well, in this case, basically, it is actually counterintuitive because we thought noble metal would be indefinitely stable on the reducing potential, but actually it's not. And the underlying mechanism can be the alkaline cation solution actually can stabilize reaction intermediates in the formation of metal hydride. Eventually, that basically contribute to the formation of this cathodic corrosion. Corrosion does mean degradation in general, but in this case, actually, cathodic corrosion is a way really is to do top-down synthesis of nanoparticles. This actually is a useful way to make bimetallic alloy without basically surfactant and ligand. So, and also you can see that way in some cases, basically we can actually get into the region which is often not accessible to like cloud synthesis, and in this case we actually can forming a bimetallic alloy here. So it's not necessarily it's not always degradation. Sometimes it can be used for nanoparticle synthesis.
Great. Dr. Yang, I can't thank you enough. Thank you so much. I'm going to connect you with those with the questions that didn't get answered today, so that you can start a conversation and they can ask a few more. But thank you. We're looking forward to your next webinar next summer. And yeah, thank you so much for agreeing to help the community and be the first in our new webinar repository series.
Thank you so much, and this is a wonderful opportunity to share our progress. I really hope like there are more people, especially young people, to join this community, and we do see a rapid growth of in terms of number of people and also like publication for this community of electrochemical STEM, and hopefully what I'm showing here is can give you some confidence of doing reliable electrochemistry in liquid cell TEM.
Yeah, there's so much valuable knowledge to be gained using the TEM. It would be a shame to not be able to utilize this technique. So thank you so much for paving the way.
Great.
Have a great afternoon, evening, morning, everybody, and we will see you next time.
Great.